Fundamental Manufacturing Processes video series, examining the tools and techniques of precision metalworking. This program is an introduction to cutting tools and tool materials. Tooling incorporates thousands of different cutting tools and tool holders for discrete parts manufacturing. Principal categories within cutting tools include single-point cutting tools, such as lathe tools, multi-point cutting tools, such as milling cutters, drills, reamers, and taps. Cutting tools are either standard tools, which are purchased as catalog items, or special tools, which are designed and built for a special machining job, often to suit a particular workpiece. The main objective in the selection and application of cutting tools is to safely machine a workpiece in the shortest possible time while meeting the part's quality requirements. Furthermore, the specified tooling should be the least costly and least complex tooling available to satisfactorily fulfill the qualitative and quantitative workpiece demands. It is estimated that nearly 50% of all cutting tools are used incorrectly. Additionally, the number one error when formulating tooling selections is calculating monetary savings based on lowest cost per tool rather than on maximized productivity and extended tool life. To effectively select tools for machining a part, a machinist must have specific information about the workpiece, such as the starting and finished shape, the hardness, the tensile strength, and abrasiveness of the material. These factors all influence the interaction between the tool and the work. The machinist also needs to know whether the workpiece material breaks into short chips easily or whether it tends to flow into long, hard-to-break stringy chips. Also important is the part's work-holding setup, which properly orientates and holds the workpiece, and the power and speed capacity of the machine tool. Changes in the workpiece material, part tolerances, geometries, and quantities required often demand corresponding changes in the tool materials and/or tool geometries selected. For the wide variety of machining applications, there is a corresponding necessity for different cutting tool materials. The ideal cutting tool material should be harder than the workpiece it is cutting, be able to retain its hardness and stability at high temperatures, resist wear and thermal shock, be impact resistant to withstand the mechanical shocks of milling, and also be chemically inert to the work material and the cutting fluid. No single cutting tool material incorporates all these qualities. Instead, trade-offs occur among the various tool materials. For example, materials with excellent chemical and thermal stability, such as ceramics, tend to be brittle, with limited resistance to mechanical and thermal shock. These variable properties take place both within a material class, such as different grades of carbide, as well as when comparing different classes of tool materials, such as high-speed steel and carbide, or carbide and ceramics. Every new and established tool material has an application area in which it outperforms the other cutting tool materials. Newer materials tend to minimize but not eliminate the application of older materials, such as high-speed steel. The development of cutting tool materials has offered steady advancement in the rate of metal removal and, consequently, in the need for more heat-resistant materials. So there has been a progression from high-speed steel to carbide to ceramics and onto other super-hard cutting tool materials. High-speed steel tools were introduced around 1900 and gradually replaced the carbon steel tools of the 19th century. High-speed steel cuts about 4 times faster than the carbon steel tools they replaced, hence the name high-speed steel. It operates at temperatures up to 600 degrees centigrade. There are over 30 grades of high-speed steel in 3 main categories: tungsten-based, molybdenum-based, and molybdenum cobalt-based. Since the 1960s, a form of high-speed steel called powder metallurgy high-speed steel has allowed tools such as drills, milling cutters, and form tools to be made to near-net shapes that offer superior grindability. The use of coatings, particularly titanium nitride, allows high-speed steel tools to cut faster and last longer. Titanium nitride provides a high surface hardness, is resistant to corrosion, and minimizes friction. In industry today, high-speed steel tools have been replaced by carbide tooling in many areas, but high-speed steel tools are still preferred for some tool room and low cutting speed operations, and for certain tool types such as small diameter drills, taps, and end mills. Carbide tools were introduced from Germany in the 1930s and today are the most widely used cutting tool materials. Carbide and coated carbide tools in general cut about 3 to 5 times faster than high-speed steel and operate at temperatures up to about 1200 degrees centigrade. Cemented carbide is a powder metal product made up of finely ground hard carbide particles cemented together by a binder. The major categories of hard carbides are tungsten carbide, titanium carbide, tantalum carbide, and niobium carbide. The hard carbide particles are from 1 to 10 microns in size and make up from 60 to 95% of the material. The binder is mostly cobalt. Variations in particle size, binder, metallurgy, and manufacturing techniques cause the properties of the carbide tools to vary widely, particularly in the balance of hardness and toughness. For example, a higher tungsten content increases the wear resistance of a carbide insert, but reduces strength. A higher percentage of cobalt binder increases strength, but lowers the wear resistance. Additions of an alloying agent, such as tantalum, can increase a carbide grade's resistance to heat, but reduces its strength. Carbide is utilized for solid round tools, such as end mills and drills, or in the form of inserts clamped to a shank or holder. Inserts may be indexed to another position when an edge has worn. When all the tool edges on an insert are dull, the insert is generally thrown away or recycled. Some inserts are single-sided, others double-sided. Every manufacturer of carbide tools has a variety of carbide grades for specific work materials and types of machining applications. Choosing the correct grade of carbide can double tool life or double the cutting speed for the same tool life. Tough, shock-resistant grades are needed for interrupted cutting. Harder and chemically stable grades are needed for finishing steel at high speed. Heat-resisting grades are needed for machining the superalloys, such as Inconel and Hastelloy. There are many considerations when selecting a carbide grade for metal cutting, such as the type of workpiece material, especially its hardness, the condition of the workpiece's outer skin. If it is a forged or cast workpiece, a tougher insert should be selected. Is the cut heavy, or is the cut light? Is the machine tool and work holding setup rigid or loose? If loose, then a stronger, more durable carbide grade should be selected. Because there are not effective U.S. or international standards for carbide grade specifications, it is the carbide suppliers who recommend which grades they believe are suitable for given applications. 2 carbide grades from different suppliers with identical coating in the International ISO 513-1991 standard will likely have different compositions, microstructures, coatings, properties, and most importantly, performance. Although carbide inserts are not standardized by application, they do carry their own 7-character ANSI code, which is used for their identification. The first character represents the insert's shape. The second character represents the insert's relief angle, which may be from 0 to 30 degrees. The third character represents the insert's tolerance class. Molded inserts usually have a code M tolerance and are the most common. The fourth character represents the type of insert with regards to its required clamping system. The fifth character designates insert size by the largest circle which can be inscribed within the perimeter of the insert, known as the inscribed circle or IC size. The sixth character represents the insert thickness. Harder materials and higher feed rates require thicker inserts to withstand the cutting forces. The seventh character represents the corner radius on turning inserts. On milling inserts, this character represents the wiper edge angle. This ANSI classification system does not categorize everything. For example, the varieties of chip breaker geometries in carbide turning inserts are not required to be covered, but many manufacturers do add a chip breaker code. 2/3 of all carbide tools used are coated, and a coated carbide should be the first tool material considered for most operations. In general, a coated carbide tool may have over 3 times the tool life of an uncoated grade, or may operate at cutting speeds 2 to 4 times higher for the same tool life. These coatings help overcome carbide's primary limitation, that is, fracture resistance or toughness increases, wear resistance or hardness decreases. These wear-resistant coatings provide carbide grades with broad application ranges, offering a combination of characteristics not obtainable with carbide alone. Most coatings are under 1/1000th of an inch thick and have several layers. Each layer has a particular benefit, such as resisting heat or decreasing friction. The main insert and cutting tool coating materials are titanium carbide, titanium nitride, aluminum oxide, and titanium carbonitride. Aluminum oxide and titanium carbide are very hard and chemically inert, and titanium nitride minimizes friction. For an appropriate coating, the coating material must adhere or bond strongly to the carbide tool surface. The 2 major coating methods are chemical vapor deposition and physical vapor deposition. The chemical vapor deposition process takes place at about 1000 degrees centigrade and is typically required for the multi-layer coatings. The physical vapor deposition method takes place at temperatures around 500 degrees centigrade and is used for single-layer or dual-layer coatings. Coated carbides are more costly on a per-insert basis than uncoated inserts, but they achieve greater productivity. In terms of parts per edge, the coated carbides have the advantage. Ceramic tools are harder and more heat-resistant than carbide tools, but also more brittle. They have been successful in machining cast iron, hard materials, and superalloys. Best results are at high speeds, which mean high cutting temperatures. Ceramic cutting tools can be divided into alumina-based ceramics and silicon nitride-based ceramics. Alumina-based ceramics are used for high-speed semi-finishing and finishing of ferrous and some non-ferrous materials. These tools are not good with aluminum because of an affinity between the materials. Alumina-based ceramics offer mechanical and chemical wear resistance, but lack toughness and thermal shock resistance. Thus, they are generally not used for milling, rough turning, or for interrupted cuts. Silicon nitride-based ceramics, also called sialons, offer greater toughness and thermal shock resistance than alumina-based ceramics. They are used in high-speed roughing applications and have excellent abrasion resistance. Silicon nitride-based ceramics are used for high-speed machining of gray cast iron, as well as on superalloys such as nickel and cobalt-based work materials. Whisker-reinforced ceramics with silicon carbide reinforcing whiskers in an aluminum oxide matrix are stronger than the brittle ceramic matrix alone. The whiskers act like rebar in concrete, adding mechanical strength and thermal conductivity. Cermet tools are composed of materials commonly applied as coatings to carbide tools, titanium carbide and titanium nitride. The solid cermet insert offers excellent resistance to various causes of wear in machining, especially chemical resistance. Initially used only for semi-finish and finish turning and boring, some cermet grades are now tough enough to handle rough turning as well as milling applications on carbon steels, stainless steels, and some ductile irons. Super hard tool materials are divided into two categories: cubic boron nitride and polycrystalline diamond. Typically, a small tip of one of these super hard materials is bonded to a carbide insert base. Super hard inserts may cost 30 times more than a carbide insert, so their use is limited to well-chosen, cost-effective applications. Cubic boron nitride, or CBN, the second hardest material after diamond, is used to provide long tool life in machining very hard, tough ferrous materials, hardened die steels, alloy steels, and hard-facing materials. CBN is a hard, brittle material requiring cutting-edge preparations to suit application needs. Other techniques are utilized to protect the cutting edge, such as the use of a lead angle, where possible, and a strong shape, such as round or square, are recommended. Polycrystalline diamond, or PCD, is composed of micro-sized diamond particles in a metallic binder and is over 50 times harder than common carbide. PCD is used for non-ferrous applications and also cuts abrasive materials such as glass, reinforced plastics, and hardwoods for furniture manufacturing. In some high-volume applications, PCD inserts have machined parts for 6 months before having to be replaced, outlasting carbide by up to 100 times. Diamond-coated carbide and ceramic inserts are a recent addition to cutting tool materials. They offer a greater variation in geometries than do PCD inserts, but like PCD, can only be used for machining non-ferrous materials. All cutting tools have a working life, and then they dull, fail, or fracture. For this reason, they are called perishable tools. The cutting tool life cycle may be a single use or involve indexing to multiple edges, as with an insert, or multiple resharpening, such as with drills, end mills, and taps. It is a safety hazard to run any cutting tool until it breaks. This creates scrap, impacts tool and part costs, and reduces productivity. Aside from breakage, cutting tools wear in many different ways. Edge wear and flank wear are both a normal and slow type of tool wear. In carbide turning of steel, it often occurs after 15 to 30 minutes of cutting. If the work material is highly abrasive, such as with certain cast irons, this type of wear will accelerate. To correct this problem, select another more abrasion-resistant tool grade. Cratering, or top wear, behind the cutting edge occurs commonly in machining long chipping steels, from abrasion and diffusion wear. If the crater grows large enough and contacts the cutting edge, the tool fails immediately. To combat cratering, use hard grades of carbide with tantalum carbide or titanium carbide and hard coatings such as aluminum oxide or other materials such as cermets or ceramics. Chipping on a tool edge is an unpredictable form of tool failure. It is sometimes started when a high point on an edge breaks away. A stronger carbide grade, different edge preparation, or lead angle change may eliminate chipping. A built-up edge is a deposit of workpiece material adhering to the rake face of the insert. Chips weld themselves to a cutting edge. Sometime later, the deposit breaks off and pulls small pieces of carbide out of the edge. This occurs at or just behind the edge. Ductile materials such as low-carbon steel, soft aluminum, and copper cause this damage. Higher rake angles, faster cutting speed, and higher pressure cutting fluid all help eliminate built-up edge. Deformation takes place at very high temperatures, 1800 to 2000 degrees Fahrenheit. These temperatures cause the insert binder material to soften, depressing the top surface and mushrooming the sides out into the clearance angle, where it is abraded away. Deformation is difficult to detect without the use of a microscope. A deformation-resistant grade and/or high hot hardness coating is required, or else reduce the operation speed to reduce the heat. Thermal cracking occurs when inserts go through a rapid heat-cool cycle, such as in either interrupted cutting or when the coolant is improperly applied, suddenly cooling a hot insert. A notch at the depth of cut line may occur in machining high-temperature alloys or with any very hard outer layer, such as in a casting or forging. This is caused by the pullout of small particles of tool material at the flank, face, and cutting edge by the pressure welding of work material to the tool material. An edge preparation on the insert and an increased lead angle may decrease notching. These are only some of the natural causes of tool wear. Maximum tool life can be achieved through selecting the proper insert or tool material or altering the cutting conditions. Let's re-examine the material contained in this videotape. The main objective in the selection and application of cutting tools is to safely machine a workpiece in the shortest possible time while meeting the part's quality requirements. There is no ideal cutting tool material, but the rapid evolution of tool materials has given us a wide choice to meet any need. High-speed steel tools are commonly used in tool rooms and in low-speed operations. Round tools such as drills, taps, and end mills are commonly made of high-speed steel. Coatings have extended the applications and cutting life of high-speed steel tools. Carbide tools, particularly coated carbides, are today's most common cutting tool material. There are a great variety of carbide compositions and coating types. Carbide tools may be indexable inserts or solid round tools such as small diameter end mills or drills. Coated carbide inserts are the first tool material to consider for most production operations. Most insert coatings have multiple layers to protect the tool against abrasion and chemical wear. Ceramic inserts may be alumina-based or silicon nitride-based. They withstand higher heat than carbide, have good resistance to abrasion, and they cut very fast. But ceramic inserts are less shock-resistant than carbide tools, so their applications are limited. Cermets are composed of titanium carbide or titanium nitride with excellent resistance to various forms of wear. But cermets do not withstand high heat well. The super hard materials are cubic boron nitride, CBN, for ferrous applications, and polycrystalline diamond, or PCD, for non-ferrous applications. Both materials are expensive, but can outlast carbides by 10 to 100 times. All cutting tools have a finite performance life. Then they wear out or fail. Hence, they are called perishable tools. The varieties of cutting tool wear include edge wear, flank wear, cratering or top wear, chipping of the tool edge, deformation, and the edge damage caused by the pulling away of material on a built-up edge. Two other types of tool wear are thermal cracking and notching.